Today what we're going to be looking at is modeling a bigger LEGO workshop example as a linear programming problem. If we look at kind of the left side of the screen right now, it has brought up the workshop example that we are interested in. Basically what we are interested in is we run a LEGO workshop, we produce small items, and then we sell them. There are 3 items that we're currently interested in making and possibly selling. And basically we have a description and picture of each of these items. So we have this T, basically requires 2 small bricks and 1 big brick. For purposes of this video, we're going to call the 2x2 bricks the small bricks and the 2x4 bricks the big bricks. Obviously there are smaller and bigger LEGO bricks out there, but easier to say small brick than 2x2 brick. So the T requires 2 small bricks, 1 big brick. It sells for $3. The cake requires 1 small brick, 1 big brick, sells for $2. And then the I requires 1 small brick and 2 big bricks, and it sells for $4. We have a limited number of bricks each week that we can procure, so we can get 200 small bricks, 200 big bricks, and what we're trying to figure out is how many T's, cakes, and I's should the workshop make per week in order to maximize its profits. So if we look at this word problem, look at this description of kind of the real-world application, the decision variables, I think, are strongly hinted at, and decision variables is always a good place to start when formulating a linear program, because the objective and the constraints will be expressed as functions of the decision variables. So we'll start with our kind of modeling this problem. We'll start by defining the variables. And basically what the variables are, we can also call them decision variables. They're mathematical representations of the decisions we are going to make. In this case, we're going to define 3 decision variables, 1 for each possible item. So we're going to define x1 to be the number of T's made per week. x2 is the number of cakes made per week. And then x3 is the number of I's made per week. So from there, basically we need to start expressing our goal, or the metric at which our decisions will be evaluated, as a function of these variables. And then also we need to express any requirements or any constraints as a function of these variables as well. So in this example, again, if we look at the objective, what our goal is, it's hinted at strongly as well. It says kind of at the bottom of the page, we want to make as much money as possible. We want to maximize our profits. So what we can start with, or start kind of thinking of, is, well, how can I express my profits in just kind of the normal English language, and then how can I translate that mathematically? So if I just kind of define my profits, well, I make profits from 3 things. I make profits from selling T's, selling cakes, and selling I's. So my profits in words can be expressed as the profits made from selling T's plus the profits made from selling cakes, and then plus the profits made from selling I's. And the reason why I kind of spelled this out is that I think it kind of helps you make the transition from the problem description to the mathematical formulation of the model. Because now, if we look at our decision variables and kind of the characteristics of the items that we're selling, we can very easily determine the profits made from selling T's in a particular week. So our profits mathematically are, I make $3 per T. So it's 3 times the number of T's I make, And I've defined mathematically that x1 is the number of teas I make per week. So it's 3x1 plus the profits made from selling cakes. I make $2 per cake, so 2x2, and then plus the profits made from selling eyes. So it's 4x3 is the profits made from selling eyes. So now I have a nice mathematical expression of profits in terms of my decision variables. So we can start kind of formally writing down our linear programming. Our objectives is we're going to maximize 3x1 plus 2x2 plus 4x3. So we have our objective. The next step is we have our objective, we have our decision variables. The next step is to start writing down the restrictions placed on our decision variables. So what are some of the things that our decisions need to satisfy? So we're going to write down subject to a set of constraints. And in terms of identifying the constraints, especially when you're talking about maximizing profits, we can start thinking about constraints as anything that would not let us make an unlimited number of teas, cakes, and eyes, or equivalently an unlimited amount of profits. So each of the items that we're making requires the use of resources. For example, a tea requires 2 small bricks and 1 big brick, and we only have 200 small bricks. So kind of as another rule of thumb in terms of trying to identify constraints, any scarce resource will have typically will have an associated constraint with it. So we can go through a similar kind of exercise looking at our constraints. We basically have a constraint that is going to say the number of small bricks used per week is less than or equal to 200, which is the number of small bricks available. Now obviously this is a constraint in words. It's not a constraint using our mathematical decision variables. So we need to make kind of a similar translation as what we did for profits to a small bricks constraint. If we look at this, we can break down the number of small bricks used per week by number of small bricks used per week for teas plus number used for cakes plus the number used for eyes. We won't write that specifically out in English, but that's what we're essentially going to do with our constraints. Each tea requires 2 small bricks. So we have 2x1. That gives us the number of small bricks used per week in terms of building teas. The cakes only require 1 small brick, so x2 gives us the number of small bricks used per week for the purposes of making cakes. x3, since we only require 1 small brick for an eye, gives us the number of small bricks used for making eyes in a particular week, and then that's going to be less than or equal to 200. I think it's kind of just good in terms of kind of formulating these models to identify. You don't necessarily need to write out number of small bricks used per week, so we're going to delete that. But just to kind of make sure that another person can come in and check the logic of your linear programming to label your constraints. So we'll label this one the small brick constraint. And then we also have big bricks. Big bricks are another scarce resource. So we're going to write another function, basically how many big bricks are used per week in terms of our decisions. So the number of big bricks used per week for a tea is simply x1. The number of big bricks used per week for purposes of making cakes is x2. And the number of big bricks per week used for purposes of making eyes is 2 times x3. And those are going to be less than or equal to 200. And then this is our big brick constraint. The last kind of scarce resource we have is that we have an upper bound on the number of teas we can sell per week. So basically, we need to make sure that we don't sell more than 40 teas. And so what this tells us is that there's an upper bound on x1. So x1 is going to be less than or equal to 40, and we can call this kind of the t upper bound constraint. So we have kind of all the listed constraints in the problem itself. The one thing that we need to make sure we also include in kind of formulating linear program, especially these examples, is any sort of non-negativity restrictions on the variables. And so we can't make a negative number of t's, cakes, or i's. What would happen if we tried to if we forgot the non-negativity restrictions on these variables is we could run into a situation where we are generating resources that we don't have available to us. So for example, if I set x2 to be -1, then what's going to happen if I look at the small brick and big brick constraints is I'm going to get one extra small brick and one extra big brick, which we don't necessarily want to happen. So we'll have x1, x2, and x3 are all greater than or equal to 0. And so these are the non-negativity constraints on our variables. And so what we've basically accomplished, if I look right now, this particular, the highlighted area is our linear programming model of our Lego Workshop example. And what we've done is we've essentially stripped away the actual application and can work completely within the mathematical world to determine what x1, x2, x3 are, which gives us the largest objective in terms of the decision variables. And then once we identify that, we can work our way backwards to actually go back to the real world based on our variable definitions to determine the number of t's, cakes, and i's made. So the next video that we're going to, the follow-up video to this one will actually be kind of implementing this linear program in order to solve it using Excel Solver. So stay tuned for that one.